Hey guys, welcome to the last discussion video on decision trees. So first let's talk about exactly what a decision tree is. So here's a picture of a decision tree from the class. Basically the way this works is at every node here we're going to split on some feature, and then at the leaf we're going to have the classification, right? So for example, imagine if I had a training point that looked like this, where patrons, weight estimate, alternate, and so on. Those are all the features of our training point. Well, basically we're just going to go through and follow our feature classifications. So here patrons is full, so I'm going to take this rightmost branch. Weight estimate is 34, which is between 30 and 60, so I'm going to go down this branch. Alternate is yes, so we're going to go down here. Friday, Saturday is yes. So now we're going to go down this right branch again, and we're going to end up at this leaf node. And once we've hit this leaf node, that's just going to be what our classification is. So for this sample, it's going to be classified as true. And that's the way our decision trees are going to work. So it's pretty simple to classify, but the challenge here for decision trees is going to be building a good one. Alright, so let's take a quick look at how we're going to formally define our decision trees. Now this is the pseudocode. So let's look at the arguments for this code first. So this is going to create a decision tree, and it's going to take in a set of examples. This is your training set. It's going to take in some attributes or your features, and then it's going to take in a default classification. So when I look at this code, I like to split it into two chunks. The first chunk will be these first three lines. So these are going to be our base cases. And this is where the leaves of the tree are created. So these are where we're going to actually assign the classifications. So let's just look at those three really quickly. So first, if you have no more examples, you just return the default classification that we pass in. Otherwise, if all the examples have the same classification, well, we can't split anymore, so we'll just make a leaf at that classification. And then otherwise, if we have no more features to split on, we'll just create a leaf that returns the classification of the most common example in that set. So these are going to be our base cases, and these are going to be how we're going to get these leaf values over here. The second half of the code is going to deal with creating our internal decision nodes. So how does this work? So first we're going to choose some feature to split on, and we'll talk more about how that happens later. We're going to create a decision tree with that feature, and then we're going to split each of the examples among the different values of this best attribute that we're splitting on. So basically we're going to have kind of n sets of examples, where example sub I is going to be all of the examples that take on value v sub I. And then each of those examples is going to form a subtree, which we can create another decision tree out of. So that's the general gist of how we're going to create our decision trees. Let's talk more about how we're going to choose our attributes. So to do this, we have to first introduce this new concept of entropy. So it's not entirely new, because I'm sure most of you guys can remember talking about this in your physics classes. So basically, entropy is going to be a measure of how random our data set is. And it's going to follow these rules. So if we have a uniform set of data, that's going to be very random, so it's going to have higher entropy. On the other hand, if our data is very concentrated, where maybe all of our data points are going to take on the same value, that's going to give us the least amount of entropy. Alright, and in order to calculate it specifically, we're going to be using this equation here. So here, we'll do an example, but just to explain this equation very quickly, here, all these P1s, P2, Pn's, these are all probabilities. So these are the probabilities of the different classifications from our training set. And then so the entropy of this training set, which has each of these probabilities for the labels, is just going to be the sum over all I, negative P sub I, times log base 2 of P sub I. Alright, so this probably looks pretty complicated right now. Let's just go through an example. Here we have the example from the lecture slides. We're just going to go through that again. And this again is the entropy equation. So first, let's calculate the entropy before the split, which is just going to be this data set here on the top. where we have 6 green dots and 6 red dots. So first, for this data set, we're going to have two P's, right? So P1 and P2. I don't know why I wrote these backwards, but it means the same thing. So P2 is going to be the probability of red, which is going to be 0.5. P1 is going to be the probability of green, which is also going to be 0.5. And that's because there's an equal number of green dots and red dots. Now we can just plug these two into our equation here, and we can calculate the entropy of this split. So the entropy of P1 and P2 as the negative P1 times log base 2 of P1 plus negative P2 times log base 2 of P2. And if you work this out, you'll find that it's equal to 1. Right? Because what we have is negative 0.5 times negative 1 plus negative 0.5 times negative 1 again, and that gives us 1. Alright, so we've calculated our entropy before the split. Now let's try calculating our entropy after the split. So how are we going to calculate the entropy here? It's going to be a bit harder, right? Because there's kind of a lot of classifications. So we have basically the entropy of the none classification, and then the entropy of the sum classification, and then the entropy of the full classification. So how we're going to deal with this is we're going to take a weighted entropy over all of the classifications. So let's take a look at how we do that. So first we're going to take the entropy of the none classification, and you'll notice that this is all uniform. So we have the probability of red is 1 and the probability of green is 0. So the entropy of anything that's uniform is always just going to be 0, right? And if you plug it into the equation, you'll be able to see why. Basically, it's because for P red, the log term is going to be 0. For P green, this first negative P sub I term is going to be 0. And that just makes the overall entropy 0. And the same is true for sum. And now the interesting one is calculating the entropy for this full classification here. And so for this one, 1/3 of the points are green, 2/3 of the points are red. So if we just plug in our values, we get an expression that looks like this. All right, and the entropy ends up being 0.92. Now we're going to take a weighted average of all the entropies. So we have 2 and 12 are going to be classified as none. So the weight for this none entropy is 2 over 12. 4 over 12 are going to be classified as sum. So the weight for sum is 4 over 12. And then 6 over 12 are going to be classified as full. So the weight here is 6 over 12. And then when we take this overall weighted entropy, we're going to be left with 0.46. All right, so let's put in our weighted entropy there. Now, when we're comparing splitting on patrons to splitting on some other classification, maybe types, we're also going to have to go through and calculate the weighted entropy after the split of splitting on types. So we're going to do that basically in the same way, where first we're going to calculate the entropy of just this fringe split here. We have a 1/2 chance of green, a 1/2 chance of red. So our entropy is again going to be this expression, which is 1. And then we have kind of the same deal for all of these other ones, where we have 50% chance of green, 50% chance of red. So we know that the entropy for each of these, for Italian, for Thai, for burger, they're all going to be 1, right? So basically from that, we know that our weighted entropy is also going to be 1. And so by using that trick, we've kind of saved a lot of work, and we already know that the entropy is going to be 1. Okay, so now we have these three values. We have the entropy before the split, which is 1. The entropy after the split on patrons, which is 0.46, and the entropy after the split on type, which is going to be 1. And now here you got to keep in mind that it's good if the entropies are low. A higher entropy means that the data is more random, and a lower entropy means that the data is more separated. So the way that we're going to see if a split is good or not is simply by looking at the difference in entropy before and after the split. And that's what we're going to call the information gain. So the information gain for splitting on patrons is going to be the entropy before the split minus the entropy after the split, which is 0.54. The information gain for splitting on type is going to be 0. And so basically this tells us that splitting on patron is a better idea than splitting on type. So in general, for our algorithm, we're going to look at the information gain for each feature and then split on the one with the highest information gain. So that's it for this week. I wish all of you the best of luck on your finals, and I hope you had a great time in CS 188.